Hello students, in last class we have done orbital speed, escape velocity and time period of the satellite. Now we are going to do some numericals. First is, imagine a light planet revolving around a very massive star in a circular orbit of radius r with a period of revolution capital T. If the gravitational force of attraction between planet and a star is proportional to r star minus pi by 2, then we have to find dependence of t square on the r. Means there are four options. First, t square is proportional to r square. B option, t square is proportional to r raised to power 7 by 2. C option, t square is proportional to r raised to power 3 by 2. And D option, t square is proportional to r raised to power 3.75. So first, it is given in the question that a planet is revolving around a star and its the radius of path is r and its period of revolution is capital T. And it is given that the gravitational force of attraction between planet and a star is proportional to r raised to power minus 5 by 2. So if it is moving in the orbital circular orbit, then there will be a centripetal force and which will be provided by the gravitational force of attraction between planet and the star. So we can write that the centripetal force mv square upon r is proportional to r raised to power minus 5 by 2. As we know that the circular orbital motion is possible only when the centripetal mv square upon r, it will be equal to gravitational force gmm upon r square, but here it is given then the force is inversely proportional to r raised to power 5 by 2. So here we will not write the r square, we will write r raised to power 5 by 2. Okay, now since it is asked in the question that we have to find dependence of the time period on the r, so here capital G and mass of the that planet and mass of that star, here all these quantities are constant, only we have to concentrate on capital T, which is time period, and it can be calculated by using the distance upon velocity. So here we are only using this relation in the form of proportionality. mv square upon r is proportional to r raised to power minus 5 by 2. So here we can write that what will be the dependence of v on the r? It will be v directly proportional to, v square is directly proportional to r raised to power minus 5 by 2 plus 1, means v square will be directly proportional to r minus 3 by 2. So v will be directly proportional to r raised to power minus 3 by 4. Here we have find that the v is proportional to the r raised to power minus 3 by 4. Now we can find that how time period will depend on r, as we know that time period is given by 2 pi r upon velocity, right? Means time period is directly proportional to r upon v, right? And we have to find the dependence of t square. So by squaring both sides, t square is proportional to r square upon v square, right? Here t square will be r square upon, as we know that v square is directly proportional to r raised to power minus 3 by 2. So here we can write r raised to power minus 3 by 2. It means t square will be proportional to r square plus 3 by 2. Means t square should be proportional to r raised to power 7 by 2. And here option B will be right. T square is proportional to r raised to power 7 by 2. Now second question. The masses and radius of Earth and Moon are m1, r1 and m2, r2 respectively. Their centers are a distance d apart. The minimum speed with which a particle of mass m should be projected from a point midway the two centers so as to escape to infinity. So, as given in the question, the masses and radius of Earth and Moon are m1 and m2, r1 and r2, and their centers are distance d apart. So we can draw a diagram. Suppose it is Earth whose mass is given, which is m1, and suppose it is Moon whose mass is given m2, and it is given that their centers are at d distance, and so we have to find the minimum speed of a particle m should be projected from a point midway the two centers. Means here suppose a point P, here that mass m is placed, and we have to find its minimum speed so as to escape to infinity. Right. Now as we know that we have to find the velocity, it means we have to find its kinetic energy, minimum kinetic energy. Okay, and by energy conservation we can apply this, and we can find out its minimum velocity. Okay, now first here potential energy of the particle m when it is placed in between the two masses, it will be, as we know by the formula, potential energy is given by minus gmm upon r. Okay, so here its potential energy due to m1, it will be minus g m1 m upon d by 2, and due to m2 will be minus g m2 m upon d by 2. Right. So net potential energy will be minus g m 2 d in bracket m1 plus m2. It will be net potential energy of the particle at this point. Means we can say due to this energy it is binded here, and if we want to want that this particle is escape from the gravitational forces between these two masses, then at least equal to this energy the kinetic energy should be provided to that particle. Means kinetic energy half mve square, here v is the minimum escape velocity for the particle, it should be equal to 2gm upon d m1 plus m2, right? So here mass will be cancelled out, and ve will be 4 by d m1 plus m2 g. So velocity will be 2 root g m1 plus m2 upon d. So it should be the escape velocity of that particle.